Welcome to Lecture 19 of Statistical Rethinking 2023. In this lecture, we're going to go back to the beginning in a way and consider the scientific foundations of statistical modeling. Let me explain.
It's a real benign aspect of the universe that linear models work at all. Linear regressions and the generalized versions of them, generalized linear models and generalized linear mixed models, have at their heart additive combinations of variables. They're the square hole of nature. And as the square hole of nature, we can use them for things that aren't square, because the square accepts all. But this is a bit disappointing from a scientific perspective, from a research perspective, because when we put the round peg in the square hole, we're giving up some scientific power. The fit is okay, but it's not ideal. We give up some statistical power on one side because the statistical model is ignoring some important features. But we also give up some opportunities to use scientific information to better inform the statistical analysis and get more that way as well.
A funny thing about cats is no matter how big they get, they're still just cats. Tigers act like house cats. They stretch like house cats. They wash themselves like house cats. They play like house cats. And linear models and generalized linear models are similar. No matter how big they get, they still have all the same fundamental properties of generalized linear models. And by that I mean they're association engines. They're not real scientific models of the mechanisms that generate phenomena in the world. They're information theoretic devices. And that's no insult, because these models are extremely useful and they've dominated this class so far, because probably more than 90% of all productive scientific modeling is done with generalized linear and generalized linear mixed models. But you have to keep in mind that these are not mechanistic causal models of scientific phenomena, and as such, they leave something on the table. Maybe we don't see this thing that's on the table. We have to look for it because the table is in darkness. But when we think hard about the scientific phenomena that we're studying, there's extra information to be had that the generalized linear models and generalized linear mixed models don't capture, because they're just engines for stratification of variables, essentially. So let me introduce you to another way of modeling scientific phenomena that starts with more basic principles and builds into estimation. So we're going to consider human height again. Remember, I said we're going to go back to the beginning, and human height was the first serious statistical problem that we looked at in this course. So here's a human being, as one might imagine a human being. And if we're going to model the relationship between body weight and stature or height, there are certain physical properties that we can take into account that arise from the structure of the human body. That the weight of a human is proportional to the volume of that human. I'll say that again. The weight of a human is proportional to the volume of that human. And so taller humans have more volume and shorter humans have less. And this is why taller people weigh more and shorter people weigh less. And of course, you're already objecting, but I know tall people who are really thin. Yes, of course, proportionality matters as well. The width matters. So some people are thinner, others are wider, and that also affects volume. And that's another thing that we have to take into account. But nevertheless, the connection between height and weight is not mysterious at all. It arises from the physics, from the shape of the human body and the nature of mass. So let's model it that way. Now, I'm going to model it in the most cartoonish way I can because I want to show you how powerful this approach is of just thinking about the scientific basis of the phenomenon and pushing statistics into the background as long as possible. Yeah. And by cartoonish, I mean, let's imagine that people are cylinders. Yeah, that the human body is just a cylinder. Yes, there are arms, and obviously you're not a cylinder. But let's start with this approximation. And this approximation is a great start because most of your volume comes from the relationship between your height and your radius, if you imagined yourself as a cylinder, which is, say, how wide you are. And the volume of a cylinder you learned at some point in secondary school and then forgot because you have a rich and enjoyable life is pi r squared times height. That is the volume of the cylinder, which is proportional to the weight. We'll deal with that in a moment, is equal to pi r squared times height. Why? Because the area of a circle is pi r squared, and then we extrude it through the height of the cylinder, h, and that gives us the volume of the cylinder. Okay, that's the volume of a cylinder, and we're going to say people have a mass that is somehow proportional to this, and this is what we're going to say. We need to express the radius in a different way. Humans don't come in every possible shape. There are no people, I shouldn't say none, there are very few people who are wider than they are tall. And so we're going to re-express the radius r as a proportion of the height, where p is some proportion of the height variable. Yeah. And this proportion will be less than a half, and we'll talk about this in a moment. And then finally, we deal with the issue of density. The way that volume of this cylinder, this human cylinder, translates into weight depends upon the density of that volume, and this translates the units of volume into units of weight. And so there's some other parameter k that we don't know, which is essentially the density. So here we have a scientific model of the most cartoonish I could imagine. I tried to think of something more cartoonish but failed, so I think this is pretty cartoonish. This is a cartoonish scientific model of the causal relationship between weight and height. Yeah. And by causal, I mean it tells us in a very specific mechanistic way how interventions on height will change weight. Yeah, and it's not, in any obvious sense, a regression model. It's a scientific model that arises from the physical structure of human bodies. We can simplify this, make it look a little bit nicer. Now here's our scientific model. The weight is equal to, we're going to say the expected weight, because of course we're going to allow for other processes that we haven't modeled to add error variation. The expected weight will be k pi p squared times h to the third. Yeah. So what do we do with this monstrosity? W is the weight. This is data. We have this, remember, from Nancy Howell's Hung data, life history data. And we have height on the far right. That is also data, courtesy of Nancy Howell. And K is some unknown density. We're going to think about that quite hard in this first part of this lecture. And P is some unknown proportionality, the proportionality of width to height, or the radius of the cylinder to its height. It'd be less than a half, right? So we need to estimate these to fit some curve. So let's make a statistical model now. I've pushed this aside long enough, but we're going to revisit the scientific model, so hang on. These are the basic components, right, that you understand. If you're going to connect any theoretical model to observations, you want to have some distribution for those observations to account for the error. Yeah, and that's what the first line in this very abstract statistical model on the slide means, that the weight of individual I has some distribution around an expected value, mu sub I, for an individual of that height. That is the second line expresses the expected weight for height. And this is the equation we've derived from first principles, just from the geometry of the human body. The third line, of course, we've got our unknowns, and sometimes called parameters, and we need to assign priors for these. They also have distributions, and we want these to be scientifically informed. And since these parameters now have real scientific natures to them. They mean particular things. This will be much easier than it is in a typical regression model. So let's work through this. Let's have a workflow. How do we set these priors? There are different ways to do it, but I think there are some good heuristics that work in lots of contexts. We want to think about measurement scales. Then we want to simulate. And third, we want to think. Now you're thinking, well, shouldn't we think first? Yes, of course, but we're thinking in every one of these steps. But you'll see what I mean when we get to number 3 by think. So let's start with number 1, choosing measurement scales. So all measurements have units typically. There's some unit measurement on them. So in our particular example, weight is measured in kilograms because we're on the metric system. And this has implications for all the other variables as well. Height is measured in cubic centimeters. Height is measured in centimeters, but height cubed is cubic centimeters, and that's on the far right. And so in order for this equation to balance, the parameter k has to have units, kilograms, divided by cubic centimeters. So those of you who haven't done physical sciences in a long time, let me explain this a little bit better. The units in an equation have to cancel in a way so that they all agree, right? So the left-hand side of the red equation on this slide has to be equal to the right-hand side. And for that to be true, K has to have units, kilograms divided by centimeters squared. Otherwise, centimeters cubed. Otherwise, centimeters cubed won't cancel, right? It has to be kilograms equals kilograms. The units have to balance. The thing about this, so I'm revving you up to think about units because I want to get rid of them, actually. Measurement scales are social constructions, and that isn't to insult them because it's impossible to have a human society without social constructions. We depend upon it. That's what we do. We're monkeys that make social constructions. But when we do scientific modeling, measurement scales often get in the way, and they're totally artifice. We can do without them. Nature doesn't know anything about kilograms. It doesn't know anything about centimeters. These are projections of the human mind onto nature. And it's always possible to divide them out and get rid of all the units and work with dimensionless quantities in your scientific models. And often, not always, but often, this makes things much easier, and it sometimes just gets rid of variables. And that's what I want to talk about here in this example. So on the right of this slide, I'm plotting weight in kilograms against height in centimeters. You think back to the second week of this course. We worked with these data, Nancy Howell's Chung data. And I've also drawn on there some dashed lines that intersect at the mean weight and mean height. And the thing about an individual average height who has average weight is that they will always be somewhere near the regression line. Yeah, and you see that here. We can always rescale any measurement by dividing it by some reference value. So in this case, I'm going to divide weight by the mean weight, and I'm going to divide height by the mean height. There's nothing special about those values. You could choose any other reference value, but it's nice to think about the means because they're close to the expectation. So here I've added a new plot on the right, which looks exactly the same, right? Your eyes are not tricking you, but the axes are different. The axes on the right are different from the axes on the left, even though everything else about the plots is the same. And this is the nature of measurement scales. They're arbitrary. So now, since I've divided weight by mean weight, weight on the plot on the right, that is the vertical axis, and the plot on the right is weight rescaled. It's dimensionless. 1 means average, and greater than 1 means proportionally greater than average, and less than 1 means proportionally less than average. And the same for height on the horizontal. This is the scaled height. 1 means average. Greater than 1 means more than average. Less than 1 means less than average. There's nothing wrong here. We've lost no information. We could always go back to the original measurement scale or any other measurement scale you like. All right, we could measure weight in stones. We could measure height in apples, and that would be perfectly fine. We haven't lost any information. Okay, what good is this? Well, I'm going to show you. I'm going to try to show you. We need to assign priors now to the unknowns. Yeah, and because the unknowns are p, the proportionality of radius to height, and k, which I called the density. And since these parameters mean something now, they have physical implications, it's much easier to think about them and assign meaningful scientific priors. It's harder in general regressions, and this is one of the things that's nice about going back to basics. So for p, the proportionality constant, what do we know about this? Well, we know it's bounded between 0 and 1 because it's a proportion. Yeah, proportions are dimensionless units between 0 and 1, and it's got to be less than a half. Yeah, because on average, but especially for the population we're modeling here, the radius of a human body modeled as a cylinder is less than a half of its height. Yeah, often quite a bit less than half. And k, the density, what do we know? Well, the most minimal thing we know is that it's a positive real number, and it's greater than 1. Yeah, so that the volume translates into kilograms in greater than 1 because of the shape of the graph we had before, the relationship between kilograms of mass and height in centimeters. So let's take a conservative approach, yeah, and not express too much constraint. Let's assign p a beta distribution, which is between 0 and 1. That's what the beta distribution does. It's a distribution for proportions. And I've chosen the values inside of this is 2550, so that the mean is a little over 0.3. Yeah, and you can see the plot of it on the right of this slide, the top red curve over there. And you might think, oh, this is a very strong prior, and actually it's not. If there's a lot of data in this sample, and this prior could easily be overpowered. But what this does is it expresses our prior knowledge that the proportion is less than a half, and probably closer to 0.25 than anything else. I mean, just think about your own body. Yeah. And then k, I assign an exponential with rate 0.5. Remember, the mean of an exponential is 1 over its rate. So the expected value in this prior is 2. Yeah. And that's the only information it contains, that it's a positive value with expected value 2. We're going to start there. Surely there are better priors that we could use, but remember, you don't have to get the perfect prior. You just have to do better than flat. Yeah, do better than no prior. And it's really easy to do better than no prior, especially when the parameters mean something scientifically. Now, as always, we do a prior predictive simulation. So the code, I hope at this point in the course, the code is not too mysterious. The first thing I do in this code is I simply sample a bunch of values, 30 in this case, for p, the proportionality constant from the beta prior, and then 30 values of k independently from the exponential prior. And then I plot them, yeah, and over on the right, this is the sort of prior expected relationships between weight and height. Yeah. There's a little bit more going on in this prior predictive simulation that I haven't talked about, so I'm going to get to that now. When we assign a distribution to weight, we need to think equally about that. Remember, even though weight is observed, the distribution we assign is a prior distribution. Yeah, I'll say that again. Even though weight is observed, the distribution we assign to it is a prior distribution. The actual residuals of weight relative to the mean mu sub I can have any distribution they like. Well, within reason. They don't have to have come from that exact distribution. This is a prior for those residuals. But we use scientific information we know about these data to assign the best prior we can, as always. And what do we know in this case? Well, we know that weight is a positive real value. There are no negative weights. Yeah. And we also know that the variance scales with the mean. That is, individuals, you have a collection of individuals who are heavier, the variance, are taller, the variance in weight among them will be greater than the variance in weight among individuals who are shorter. That's just a natural feature of the way the scaling works. So we want some distribution that has that relationship. And there are several to choose from. The most convenient is just the log normal. And the log normal makes a lot of sense. Long ago in this course, I explained, and I say something about this in the book, growth is a multiplicative process, right? If you have fast growth early on, that makes later growth more powerful because there are just more cells to divide. And multiplicative growth processes generate log normal distributions. And so we can just use a log normal distribution here. The weird thing about log normal, I have to note for you, and this catches me up every time I work on a project that has a log normal distribution. The log normal is parameterized with two parameters, mu and sigma. So it looks like a normal distribution, but those are the parameters of the normal distribution, that you get by logging. I'll say that again. The mu and the sigma inside the log normal there are the parameters of the normal distribution that you get by logging the outcome variable. They're not the parameters of the log normal. The mean of a log normal is a function of both mu and sigma. Now, I'll say that again because this always confuses me. The mean of a log normal is a function of both mu and sigma. But the mean of the normal distribution you get by logging W is just mu. So when we model this, our scientific model, this k pi p squared h cubed, we need to put an exponential link on it, on mu, because this is the expected value of weight on the natural scale, not on the log scale. I know this is weird. Think about it for a moment, and you're going to work with the code, and you'll get it. I'm very confident. Here's the code. So we set up a simple data list, and this is just a log normal distribution. DL norm is log normal. And then I just write the exponential link, and I write in pi manually. You don't have to do that, but I think it makes it easier to parse what's going on in the code. And then k p squared h cubed, and then the priors we talked about before. And this is the fit we get from this. And you can tell it's not perfect, but that's okay. This is not bad for a cylinder. I told you I wanted to use the most cartoonish and feeble scientific model of human height, how human height influences human weight that I could. But this gets most of it, seemingly almost for free. But it's fitting children quite badly, and you'll see the expected curve misses the data at the lower end. So something interesting is going on there. And the good news is, in a model like this, errors are much more informative because the direction of the error tells you something in relation to the scientific parameters. In a general regression model, which is just a curve fitting exercise, failures don't immediately tell you something about what's gone wrong. But in a model like this with scientific structure, we get clues. So in this case, the proportionality is different for kids, right? It's probably not their density. It's their proportionality, that is the ratio of their height to their width, to their radius, as it were, is different. And that makes a lot of sense. And so if we were going to try to improve this, we would start there. If you just have epicyclical models like regressions, multiple regressions, it's much harder to learn from the prediction errors. Okay, so that's already pretty good, but we can do even better by thinking about this for a second. So let's come back to the basics. Here's the expected weight for a given height h. And if we take the posterior samples from the model we just ran, the joint posterior distribution of the two parameters, k and p, are very weird. Here they are. or rather k and p squared, are very weird. Yeah, and remember, these are the only two unknowns. We've only got two parameters, k and p squared. Well, there's the sigma in the log normal, but we'll leave that aside because that's an error variance thing. So k versus p squared, and you'll see there's just basically just a curve that expresses the relationship between k and p squared. What's going on here? Well, what's going on here is that these parameters are completely unnecessary. And they can be completely described by a mathematical function that in a sense is already known by the equation we've written down. And Bayes has discovered it through the implications of probability theory, because Bayes is very clever. But let's get rid of these parameters now. Let me show you how. Okay, here's the idea. So remember, I rescaled weight by dividing it by the mean weight and height by dividing it by the mean height, such that the mean weight is now 1 and the mean height is 1 as well. And so let's consider an individual at the mean weight and height. So I've replaced mu with 1 and height with 1. And this is perfectly fine. We're just going to think about this equation for a moment. And now we can ask, under what values of the unknowns is this still true? Yeah? In fact, we can solve for k in terms of the other variables just by doing a little bit of algebra. And so if you solve the second equation on the screen for k, you get the third equation on the screen, k equals 1 over pi p squared. And if we plot this function on the graph, well, lo and behold, it follows the posterior samples for the most part. There's a little bit of offset there due to the log normal error variance. But this is the sort of thing you get almost for free from scientific modeling, is that there is a built-in relationship between k and p squared that must be true, that simply arises from the nature of the variables and the fact that we used a volumetric cylinder. It gets even better, so hang on. So again, on the slide, there are three equations now. I'm going to work from the top to the bottom. The first one is just the thing we had before. We consider an individual of an average weight, that's the one on the left, and an average height, that's the one on the right. If we replace k with 1 over p squared, then we get the second line, but I've replaced the unknown, that is with this kind of joint parameter theta. Or another way to say this is a better way to say it. K times p squared is some value. And whatever its value is, it needs to satisfy this equation. Yeah, you don't even have to think about the k equals 1 over pi p squared anymore. It's just that there's a product, k times p squared, and we're going to call that product theta. What does theta equal? Well, in order for that equation to be satisfied, it must be approximately 1 over pi, or pi to the minus 1. Otherwise, the equation won't be true. Yeah. Theta has to essentially get rid of pi in order for the left-hand side, which equals 1, to be equal to the right-hand side, which also equals 1. Yeah. And so there are no parameters in this model. There are no free parameters to estimate. So let's estimate it that way. Here's a new version of the cylinder model of human weight and height. And you'll notice it has no parameters except for the sigma error variance in the log normal. But the expected value there, exponentiation of mu, is just the cube of height. And that's it. Yeah, cube because it's a volume. Yeah. And we can fit this, and lo and behold, we get almost exactly the same curve as we got before with two free parameters. Yeah, two useless free parameters. Yeah, that were there simply because we hadn't thought hard enough about the equation. Or rather, I hadn't. Yeah, don't want to put this on you. This is a really cool thing, I think, that arises from basic geometric relationships. It's a field called allometry, and lots of things happen. And once you get rid of the measurement units on things, there are these fundamental scaling relationships between quantities that emerge, and often you don't need any free parameters at all to create quite useful predictions about the relationships between these measurements. Obviously, we could do better here because we're still missing the kids, and there's more that we can do because we've left out some very reasonable biological assumptions, like the proportions of the body change over time. The density might as well. But that's all good because we've already got pointers, because this is a real scientific model and not just some cartoon regression. Okay, let me try to summarize this. I know this might have been a bit weird. Most of the relationship by which height influences weight is just the relationship between the length of some shape, not exactly a cylinder, but something like that, and its volume. So changes in body shape. We had some error in the posterior predictions, and it's likely that changes in body shape will help us do better there. You might want to play around with that and see what you could do. The idea would be that the proportionality P changes with age. And the overall lesson I want you to take from this is not so much the details of this example, although those are worth studying because allometry is a very general phenomenon in lots of ways. It also applies to metabolism and other very important features of health and growth. But rather that when we postpone thinking statistically as long as possible, often we end up with a better statistical model. I'll say that again. When we postpone thinking statistically as long as possible, often we end up with a better statistical model. Yeah, and there's no way to do good empiricism without thinking theoretically about what you're measuring. Okay, let's take a break, review the slides here, jot down some things that might have been confusing or not. Go for a walk, take care of yourself, and when you come back, as always, I will still be here. In the second part of this course, I want to talk about a different kind of scientific model, and I want to introduce it by introducing the experiment that generates the data. So what you're looking at here is a cartoon version of a device developed by some mad developmental psychologists who are interested in how children learn from one another, particularly in low information settings. And so this device accepts tokens and it dispenses toys. And there are 3 tubes. Children are given tokens and they can put them in any of the tubes freely of their choice. And all of them dispense the same toy, but the children don't know that. So put yourselves in the shoes of an observing child who is sort of the experimental participant, if you will. And your behavior is going to be measured. And what you get to see first, before you interact with this device, is a child come up and put a token in the red tube and receive a toy. And then that child goes away, and a new child comes up and also puts a token in the red tube and receives a toy. And then a third child comes up and puts a token again in the red tube and receives a toy. And then another child comes along and puts their token in a different color, let's say yellow. And then the same child, again in yellow, and again in yellow. So this fourth child that you've observed gets 3 toys, all from the yellow tube. And now the question is, what do you do when you get your token? We give you a token and we invite you to insert it in one of these tubes. What do you do? Now, since the people that ran this experiment are psychologists, everything is counterbalanced, right? So what we wanted to think about is that the 3 kids at the top of this slide are the majority demonstrators. They're demonstrating a choice, the red tube, that the majority of children chose. And the child at the bottom is the minority demonstrator. but the total amount of evidence for both colors is the same. That is the number of choices, and that's an important feature of this experiment. Yeah, but the minority demonstrator is not always after the majority demonstrators. This is also sometimes counterbalanced across kids because psychologists are good at experiments. And so a lot of kids were put through this experiment in multiple countries, and our job now is to try and figure out what strategies they're using to make their choices. That is how they learn, if at all, from the observations of the other kids. And there are three choices that can be made, and we're going to think about these colors in terms of the majority choice, whatever the majority color was, the minority choice, whatever that was. In my example, it was yellow, but it could have been blue in any particular experiment. And then there's the unchosen color, the color that was not demonstrated by any child. And these are the only three observations that can be produced by a single participant. But here's the cool trick. Our question is whether children copy the majority or the minority or ignore them. Yeah, and there are lots of good scientific questions that pivot around this issue of majority choice. The problem is that we can't see strategy. Strategy is a latent variable. It's unobservable. Now, all we see is choice. And if a child is copying the majority, that choice will be consistent with other strategies as well. Yeah. For example, suppose a child chooses a random color. They ignore the other children completely and just choose their favorite color, and favorite colors vary among kids. Just by chance, they'll follow the majority a third of the time, which is not an inconsequential probability at all. Say they just choose a random demonstrator, one of the four kids. Three of them demonstrated the same color, so now they'll follow the majority 3/4 of the time. But they're not actually following the majority. They're just choosing a child at random to follow, maybe because they liked the barrette or hairband that they were wearing. And then another third example, just a random demonstration. Right, there are 6 demonstrations of putting a token in a tube. 3 of them were the majority choice, and 3 of them were the minority choice. So if you just choose a random demonstration, you would follow the majority half the time. So you see that there are lots of strategies that have substantial probabilities of looking like majority choice. And so how do we deal with problems like this? Well, we think scientifically, and we build up a generative model of those strategies. Here's just a simple simulation to reinforce what I tried to explain on the previous slide. We imagine that children choose a color at random. They completely ignore the demonstrators, and that's what I'm simulating on the left. And then I just... so what am I doing here? Sorry. Half of the children choose a random color and half follow the majority. And we observe a total sample that is a mixture of these two strategies, and then I show you the simulated data on the right. And yes, there are more choices consistent with majority strategy, but a lot of them are just random choosers, and so the total evidence for majority influence is exaggerated, and this is not good, right? Because we'll reach the wrong conclusions. So we can't just use the choice as a proxy for strategy because multiple strategies produce similar choices, can produce the same choices. This is like in the very first lecture of this course when I tried to emphasize that in any even moderately complicated scientific context, null models don't work very well. And that's because many different non-null models will produce the same observations. Yeah, as null models and as one another. So in this case, a majority choice does not necessarily indicate majority preference. There are lots of other strategies that could also explain the same observation. So I want to develop a statistical model for you that deals with this as an example. And of course, there are lots of strategies you could dream up. This is part of the fun of scientific modeling. I'm going to consider 5, which I know maybe sounds like a lot, but you could probably think of some more by the end of this section. The first is majority choice. That is, that the child follows the choice that was chosen by the greatest number of children. The second is the minority choice. That is, the child follows the choice chosen by the minority demonstrator. That is the child that chose the other color. Third, I'm going to call maverick. What does that mean? Well, the maverick choice is you choose the unchosen color. You want to see what happens because none of the demonstrators chose it. 4 would be the random color choice. This means you ignore the kids completely and you just choose a 2-bit random. What does random mean here? Well, as always in statistics, it just means we don't know what explains the choice, but it doesn't have to do with the demonstrators. Yeah, it could be favorite color or something like that. And then a 5th one is you just copy the first demonstrator. Whatever the first child chose, just copy them, and then you got bored and stopped paying attention, and you just go with that. You can probably think of others like follow last, right? And you could try to program those by the end of this. Okay, how do we build a stat model like this? This is going to be what's called a state-based model. And in a state-based model, there's some latent generative level that generates observations, but we start by thinking about the observations, and they come from a categorical distribution. The idea here is that there are 3 possible observations for each child. Either they choose the unchosen color, and we're going to code that as 1. The majority, we're going to code that as 2, or the minority, we'll code that as 3. And those are the only 3 possible observations. Those observations can be generated by different latent states that the children occupy, and in this particular model, those states are their strategies. These categorical distributions are parameterized by a vector, and this vector is of the same length as the number of outcomes. So in this case, theta is a vector with 3 probabilities in it, and each corresponds to the probability of each choice. So we have to model that vector. So here it is. I'm going to walk through this slow, so don't panic. Each element, j of theta, j can take the values 1, 2, or 3, is equal to this weird thing on the right. And I'm going to explain this to you step by step, what it means. The first part of it, this big sigma, is just a sum. What we're going to do is we're going to sum over all the possible strategies. And we do this because we're computing an average, right? So we don't know which strategy the child is using. And as always in probability theory, when you don't know, you have to average or marginalize over your uncertainty. And that's what this sigma is going to do. So capital S is just an indicator variable for a strategy, and it ranges from 1 to 5, the 5 strategies from the previous slide. The next element of this equation is P sub S, which is the prior probability of strategy S. Yeah, that a child uses it. And then finally, this PR Y equals J conditional on S. This is the probability that choice J arises, or J is 1, 2, or 3, assuming strategy S. Yeah, we don't know that a child is using strategy S, but we do know that if they did use strategy S, we could say what the probability is that this choice would arise. So this expression here is purely mechanistic, and we just get to write it in. We know it because we've defined the strategies. It's not something to be estimated at all. That'll be a little bit clearer when I show you the code, but first we need a prior. We need a prior over the vector P, which is the prior for the strategy space. And in this example, I'm just going to make it so that every strategy has the same prior probability. You'll remember in an earlier lecture when I introduced ordered categorical predictors, I introduced this Dirichlet distribution, which is a distribution for probability distributions. If you've forgotten that, you can go look it up later. This is just to say that I'm not assuming that any one of the strategies is more plausible a priori than the others. The data will tell a different story, though. Okay, this kind of model is extremely awkward to code. I'm sorry, it's just the truth. But there's a lot that you get from coding it. And this is, I think, the first model in the course this year that I'm going to just show you with raw stand code. You don't have to understand every detail. A stand model, that's what you're looking at on the left. This is the kind of code that my R package and the ulam function generates for you. It compiles into a stand model, and then stand does the sampling. And we're looking at the raw stand model. If you code stand directly, often it's much more expressive and you can do trickier things more easily. And the thing about a stand model is you have to explicitly declare at the very top the data and then the parameters. The data are the observed variables and the parameters are the unobserved ones. Yeah, and so you see right here we have this observed variable y, which are the choices of each child. These are our values 1, 2, or 3. And then the unknown thing, the only unknown in this, are the proportions of strategies in the sample of kids. And we start with a simplex. Remember, simplex is a vector that sums to 1. Yeah, so it's a probability distribution. And that's what we declare here, a simplex of length 5 named P. And then we come down to the model block, which is the code that does the stuff you're usually used to. I declare this essentially throwaway vector theta, which is not a parameter, it's just our linear model, right? And so it's a vector of length 5. And here's the prior, yeah, Dirichlet prior. And then here's the action. And you don't have to understand every bit of this notation. I know it looks like a lot. I just want you to understand that all this code is doing is it's saying for each observation, we're going to fill in the vector theta based upon the logic of each strategy. I'll say that again. For each element of the vector theta, remember the vector theta contains the probability of the observation for any particular child, conditional on assuming a particular strategy. So there are 5 slots in theta, and all we do is we work through them, and we say what's the logic of each particular strategy, and given that logic, what's the probability it would have produced this observation. So the first thing there for majority, yeah, you see if y sub I is the observation, if it equals 2, which is the majority choice, then the theta for majority equals 1, right? Because if a child is following majority strategy, the probability they will choose the majority color is 100%. And then similar for the minority strategy, just below it, in that case it would be y sub I equals 3. Otherwise it's 0, right? And then the maverick is the final color. If y sub I equals 1, that's the unchosen color. Maverick is guaranteed to choose it. Yeah. Remember, we don't know that children are using these strategies. We're going to average over that lack of knowledge in a little bit. The random color there is 1/3, and that's what theta sub j4 is, theta sub 4. And then there's follow first. And follow first depends upon whether the minority or majority color went first, and there's a variable in the data set for that. Okay. And then there's the calculations, doing math in computer, and we have to do everything on the log scale. So we take this whole expression now and we compute it on the log scale. Remember, multiplication on the log scale is addition, and so it's the log of p sub s plus the log of the particular theta sub js that we needed. And this gives us the proper sum, or the element of the sum. And then we add them all together at the very bottom with this thing called log sum exponent theta j, and then that theta j is fed into the top. Yeah, and that's the thing we update with, right? The categorical distribution is updated right there, and that's what the target on the left means. Okay, if you run that model, it samples just fine. It has no problem, and you look at the posterior distribution, the marginal posterior distribution of each element of the vector P, and this is what it looks like with 89% plausibility intervals. There's good amount of evidence for majority choice, but you see that all the strategies remain plausible. There's just more evidence for majority and follow first than for the others. And random color, that's what color means, random color has a really wide plausibility interval. And the meaning of that, I think, is easier if instead we draw samples here, right? Because these, the elements appear correlated with one another. Yeah, and that's very hard to see in a static plot like this. But say I draw I do posterior draws for the vector P, and I animate them as I'm doing here, and you'll see that if you look at the color column, it varies a lot more. And if it goes up high, then the others have to get lower, and if it goes low, that probability gets reallocated to the others. But it has a much larger variance than the others. Yeah, and that's because it's random. It can always explain away. Random choice can always explain away the others, and the data are not sufficient to exclude it because the experiment wasn't designed to exclude random choice. That wasn't what it was probing. Nevertheless, the possibility of random choice haunts the experimental design, as you see here. Yeah. Then you can see the differences. The majority is consistently more plausible than minority choice in this, and there's lots of evidence also for following the first. That is, whatever color the first demonstrator chose. Okay, let me try to summarize a bit about state-based models. This has been a very specific example, and it's related to developmental psychology, and maybe you're not interested in that, but there's a really big space of models that have these same properties, where the basic idea is the thing you want to learn about is some latent state. It doesn't necessarily have to be a strategy. It could be a location, wealth, all kinds of things, knowledge, intentions. These are unobservable things. But you have what is called in this business emissions from those latent states. Emissions are behaviors or any kind of observable variable. And even though more than one latent state is consistent with any particular emission and with any particular observation, if you get enough data structured in the right way, you can still learn things from the sample. And that's what we've done here. Yeah. Now, the alternative to doing this is just to analyze the data wrong, right? So what you can imagine doing is just running a categorical regression on the outcomes, majority, minority, unchosen, and just saying every child that chose majority is following the majority. But that would be wrong. That would exaggerate the evidence for majority influence. So we have no choice, once we're aware of this, but to do the right thing and use a state-based model. State-based models are incredibly common. They're applied to movement, learning, population dynamics. In fact, after the next break, that's what we're going to look at. International relations, family planning. All kinds of examples are state-based. So the last example, let me say a little bit more before the break, family planning. How is family planning a state-based model? Well, a particular individual or a couple may have intentions about the size of the family they want, but pregnancy and child-rearing are to some extent stochastic, and so those intentions aren't always realized. And so any realized family size can be the product of multiple family planning strategies. Yeah. And so if you want to study how people are strategizing about the growth of their family, it's not sufficient just to count their kids. Yeah. Okay. Let's take another break and again review the slides. I know the first two sections of this lecture have been completely different from one another, and both of them have also been completely different from everything else in the course. I sympathize. So take a quick review and then take a break. Take care of yourself, and I'll be waiting here for you to come back. Welcome back. In this third and last section of this lecture, I want to show you another kind of state-based model, but this one is quite different because it has dynamics to it. It varies in time. Usually, this kind of model is discussed as a population dynamics model. And there are many different applications, but I'm going to use an ecological example. So the classic ecological example, going back a few hundred years now, is the study of how species influence one another in ecological systems. Some animals eat other animals, and therefore they depend upon them. And the quantities of these, the numbers of these different animals vary over time, and they influence one another causally as a result. And so, for example, the lynx on the right-hand side of this slide does not eat grass. He's too proud. He does eat hares and other smaller animals. And if there are fewer hares, then the lynx go hungry, and there will be fewer lynx. When there are fewer lynx, the hares do better because they're not getting eaten, and they may increase in number. But as they increase in number, the lynx do better. And this leads to interesting reciprocal causal processes. So this will also be a chance for us to think about cases where instead of a directed acyclic graph, this process would be cyclic. But because we're going to model it in time, there are no cycles. They're simply reciprocal causation feeding forward in time between the different species. And what we're interested in estimating is exactly how the different species influence one another, what their interactions look like, to what extent do lynx depress hare numbers, for example. So here's the cartoon version of it, thinking about it, and this is the sample we're going to use. This is a somewhat famous or infamous, depending upon your opinion, historical example from Canada. From the years 1900 to 1920, there are records of numbers of pelts that are recorded from trapping hares and lynx in different parts of Canada. And I show the hare in trend in black. Remember, this is numbers of pelts. This is not the numbers of animals, and this is thousands of pelts. And then the lynx in red. And sure looks like there's some relationship between these two things, and how might we explain this with a more foundational scientific model, and how might we learn something about the unknowns in such a model from these data? Well, the most basic and cartoonish, certainly not scientifically satisfactory these days, but you got to start somewhere in this business. Process model of the relationships between a pair of species is the so-called Lotka-Volterra ordinary differential equations, and that's what I put on the slide here. And let me walk you through these just to understand. These are very simple once you get used to them. So the first thing to understand is there's one equation for each species, and each of these equations doesn't specify the number, but the change in number. I'll say that again. Each equation does not specify the number of hare or the number of lynx, but the change in number with time. And that's what the dH over dt is, and the up there, that's the change in the number of hares with respect to time, and the dL over dt is the change in the number of lynx with respect to time. And then the next thing we have in these equations, so just look at the hare one for now at the top. We have the number of hare at time t times their birth rate, because hare only come from hare. Yeah, they don't come from the soil, right? They don't sprout forth from lettuce. If you don't have any hare, you don't get any hare. And then they're removed from the population through death. And this is a fundamental fact of just how biology works, and we know it's true. And if there are no hare, H sub t, then they can't die. And so the change in the number of hare with respect to time is equal to that difference. And the same is true logically for lynx. Okay, now we start parameterizing it to put in causes of interest. Births are caused by lots of things and deaths by lots of things, and we're going to focus on just a few things here. We're going to have some parameter, b sub h, for the birth rate of hares. Yeah, and we're going to make that independent of the lynx. The idea is that lynx don't depress births of hares, but they do increase mortality. And that's what we have on the right-hand side of this equation. Now we have the number of hairs h sub t times L sub t, which is the number of links at time sub t, times m sub h, which is the impact of links on hairs, right? It's the sort of force of mortality that links put on hairs. Yeah. Now, obviously, this is not completely realistic, yeah, because this equation says if there are no links, then the hairs don't die, right? And you know that's not true. But put that away in your mind pocket, yeah, and let's continue with the lesson. Obviously, we can do more complicated models, but I'm trying to do something that is conceptually easy to grasp here. And then similar logic for the links. We want their birth rate to depend upon the number of hair, because if the links don't eat, then they can't get pregnant and they can't nurse their kittens. Our baby links called kittens? I hope so. So it's L sub t times H sub t times B sub L, where B sub L is the extent to which the birth rate is proportional to the number of hairs. And then we subtract some natural mortality of links that doesn't depend upon the hairs, and there's just a constant m sub L for the mortality rate of links. Okay, a lot on the slide here. Hang on, I'm going to walk through it piece by piece again. We're going to have two vectors of observed variables, the numbers of hairs at each time t and the number of links at each time t to explain, and we need symmetrical models for each of them. These are positive numbers of pelts, right? The little h sub t is the number of hair pelts at time sub t, and the little l sub t is the number of links pelts at time sub t. And these have observation error on them, and the log normal distributions express that. And the mean of these log normal distributions is, our theoretical model. It's the log of the true number of hairs, capital H sub t, times some parameter p sub h, which is the probability a hair gets trapped, essentially. Yeah, some proportionality. And it's logged because it's a log normal distribution. Yeah. And remember, log normal distribution is parameterized for the normal distribution that you get by logging. And so there's logs everywhere. I know, it's not fun. But otherwise, that's the standard. Then I repeat the differential equations, those dH dt and dL dt's, and we get an expected value for the number of hairs or the number of links at any particular time t by integrating using that differential equation. So what does this mean? Well, it just means summing up in continuous time all the population changes up until that observation time. And so that's what we get at the bottom here. The expectation for h at some time t is any initial observation, h sub 1, plus all the accumulated changes arising from the population dynamical model. Yeah, and that's all that weird-looking slinky S is. It sums from 1 to t using the changes dH over dt. And that's all that means. Okay, let's do prior simulation before we fit the data. So this model is capable of producing a really wide range of population dynamics. And I'm just sampling from the prior here to show you that you have to do some prior predictive simulation to get this to do anything even remotely reasonable for real animals. But they're biological parameters, right? So the birth rate for hares needs to exceed their death rate, for example, at least in the absence of links, and so on. So here I'm just showing you this animation, sampling from the prior distribution to show you that you get, with time on the horizontal axis, this kind of feedback effect from this model quite easily, where hares reach a maximum and then links increase, links in red, and this leads to a decline in hair, then a decline in links, and then it repeats, potentially forever. Again, a stand model, and you don't need to understand all the details here, but I think it's nice to expose you to the idea of what's really going on inside the box. What goes on in this kind of model, which is called an ordinary differential equation model, is that you need some function that, well, returns the rates. That is, just computes the differential equations, the rates of change. And the way you do this in Stan is you write a subfunction shown here at the top of this code block, and it feeds in all the data and the necessary parameters at the top. And then all it does is plug those into those differential equations, which are the ones we saw before. These may not look exactly the same to you, but that's just because I've simplified them to reduce the numbers of multiplications that are necessary. I've factored out H and L respectively in each of them because they're present in both terms. Yeah, but this is all that's going on here, is just that. And then the action down here is to do the integration. So Stan has an ODE solver built into it, like all kinds of packages that let you do this kind of modeling. And you just need to tell it the function that contains the differential equations, and it'll do the cumulative calculation for you of the expected cumulative change from any one time point to another. And that's what's going on in this block. Again, the details you can learn later. Don't stress about it. I just want you to understand the conceptual function of this code. And then there's the observation model, where we deal with the fact that we haven't observed the number of hair and lynx. Instead, we've observed pelts, and pelts are not a perfect indicator. And that's what's going on in here with the log normal distributions. At each time t for each species k, we predict the number of pelts that were observed using a log normal with a particular air variance for each species and a different proportionality, different population predictions in POP, and that comes from the integrating the ODE, and then a different proportionality P, that's like a trapping probability for each species K. Okay, and this is what we get. Now I'm showing you the data in the points are the data, red for lynx and black for hair. And I'm sampling from the posterior distribution now to do the animations. And you'll see, first of all, yes, you do get that pattern that looks like a feedback. That's what this model tends to generate. There's a lot of uncertainty, as you'll see, because the curve is not fixed to the observed points because of the measurement error that's assumed in the model, yeah, which is the right thing to do. Yeah, we didn't observe hair and lynx, we observed their pelts. And so you get a lot of different dynamics that are consistent with this, but the dominant one is that is this predator-prey interaction, as it's called. Okay. Many other more complicated and much more realistic ecological models are possible here, and those are the sort of things that ecologists work on. I don't think anyone really uses basic Lotka-Voltaire anymore, but if you want to do this sort of modeling, that's where you start. To say that real ecologies are much more complex, but we don't understand them by trying to confront all that complexity at the start. So what do I mean when I say more complex? Well, for example, there are other animals that eat hair. Hair are, it's sad to say it, but they are delicious, and many things will eat them. It's not just lynx. And so we may want to think about that as well, that their population dynamics are driven by other predators, including people. And but the general point is, if you don't have a causal model, there's really not much hope of understanding ecological interventions, right? So if your goal is to manage the population so that you can hunt it sustainably, or to do some sort of conservation interaction, ecologies are complicated things, and if you don't think carefully about these things in a causal structure, not a generalized linear structure, but a real nonlinear causal structure. This model is definitely not linear. You're unlikely to predict the consequences of interventions very accurately. Yeah, and this framework, this general framework, the details are different, but this general framework has been extremely successful in managing fisheries. Yeah, so this idea that fisheries are managed poorly, but actually on average, they're managed extremely well and sustainably, right? Because what nations want to do is they want to keep harvesting fish from their fisheries forever, and that's how they manage them. There are fisheries that are managed badly, but by and large, professional ecologists, fisheries ecologists do a very good job using mathematics like this to set catch limits, and so on. This basic kind of modeling is useful in lots of other ways too. This isn't just for ecological dynamics. There are lots of there's a whole branch of ODE modeling that it's called pharmacokinetics, which has to do with studying how medicine diffuses through the human body, and it's extremely important in developing medications and understanding side effects. Okay, this has been a long lecture, and we started with a lot of disappointment thinking about generalized linear models. And what I've tried to do is show you not that generalized linear models are bad, because there are square pegs that go in square holes, and that's what we should do with them. And sometimes just when getting a project started, it's fine to use generalized linear models as well. But eventually, in mature sciences, we move beyond that, and we have bespoke causal models scientifically tailored to particular problems. We put our round pegs in our round holes, and this brings elation. Every field has its own problems with measurement and its own sorts of complicated time dynamic phenomena that it's studying, and so every field is going to need its own statistics. But if every field is just using t-tests and linear regressions, then they will never be able to live up to their scientific potential. Of course, it's true as well that it takes a long time for every science to develop those candidate tools. And so if any particular science is having statistical frustrations, that doesn't mean it's hopeless. And if you are ever having particular statistical frustrations, that doesn't mean you have no hope. All right. This has been a strange trip. The three sections of this lecture are almost maximally different from one another, but I hope you've enjoyed the tour, and I hope I've convinced you that there's a lot of value that comes from postponing doing statistics as long as possible and thinking scientifically, doing theory development with statistics far, far in the background. The epicycles can be extremely effective when you don't know enough about a scientific domain to really do any theory. But once you have some domain knowledge, you can do much, much better by just throwing the epicycles away. One of the ways in which scientific models are better is that when they're wrong, and they will be, they'll make bad predictions in some way. The nature of the wrongness, the nature of the mistake, tells you something, because the variables in scientific models are meaningful. They're not just associations. Yeah. This stuff is hard, though. It's typically much easier to just boot up a multiple regression and get to work describing associations than it is to develop a real scientific model. But it's worth the effort. But you have to be patient with yourself. It takes time. You want to start by studying other people's models and build simple cartoonish models, like, for example, that the human body is a cylinder to start. And then you scaffold your way up. You start with easy things, and then eventually you're a master yourself, and you teach your own students. As with all complicated things, I know I've said this almost in every lecture in this course, if it's complicated, that means you have to take it slow, and you have to work in a way that is safe. Yeah, that you use tests, you verify that the code could work on synthetic data, and so on. And I apologize for not always showing that detail in every lecture, because the lectures would be too long. But in your own research, it's really essential to do that. And the good news about doing that, it is extra work, but you'll feel much better. You'll have much more confidence that the code is working, and you'll gain a bunch of insight from the exercise of writing a generative simulation as well. Okay, that has been the 19th lecture of Statistical Rethinking 2023. We've just got one more to go. And in the next lecture, I'm going to talk about a bunch of, sociological stuff that sort of envelops statistics in the sciences. And I hope you'll join me.